Hello, welcome back. Okay, we continue with complex integration. Today we have a simple lecture on how to calculate simple residues, and I call it simple because we'll have a lot more complicated stuff when we go to actual integrals. Okay, so just to give us an idea, I think I've got a list of about 8 up there to go through. They're all very quick, just to see the basic technique for doing so. And if you want to follow some of this work and more of that, of course, you can actually find work such as this if you go to my website and you go into booklets, advanced, and I think I have this work under residues and applications in integration or something along those lines, so you can find the whole book with stuff like that in there. Okay, apologies for my mic. It's a new mic again. I'm very conscious. It has sometimes it does some squeaking noises or almost, and sometimes farting noises. It's not me, I promise you. Okay, so just I hope it's behaving today. Where is it? It's there. I think it's when it's rubbing on me, or it picks up other bits. Okay, let's get going with this particular work. I've written here 2 formulas. First of all, which I'm going to refer to. This is the general formula for finding, for computing residues for poles of order n. There won't be poles of order n. There'll be sort of like double poles and triple poles and so on at best. And I've got, of course, the special case down here, which is for simple poles, which most of them will be simple. Okay, so that's this formula where n is equal to 1. Okay, and we're gonna use these two results, as well as actually sometimes we'll be finding residues from the Laurent expansions directly. So the first particular thing that we're going to do, I've got the list up here. The function is, I'm gonna have to move it here because I can barely read it. Okay, is f of z is equal to 2z plus 1 over z squared minus z minus 2, and we want to find the residue of this function at its poles. So first of all, we need to see what kind of poles it has. This is quite clearly factorizable. It's quadratic. It's actually factorized over the reals, so it's a 2 times 1 plus 1 minus, and therefore it's like this. The top, of course, doesn't make any difference. So we have simple poles at +2 and -1. Okay, so we're going to use this formula here for simple poles. So I suggest you write it down, have it in front of you somewhere, because occasionally I might be covering my body as I'm writing on this side of the board. So first of all, the residue of f at, we're going to do the 2 first, is the limit as z tends to 2, z minus 2 times my f of z. So my f of z is, of course, 2z plus 1 over z minus 2, z plus 1. The z minus 2 is gone. So this limit can be evaluated now. I'm just going to write it here. When we put in 2 times 2 is 4, 5 on the top, and at the bottom I've got 3. So the residue at the pole at 2 is 5/3. And we've got one more residue to calculate. That is the residue of f at the simple pole at -1. Both of these poles are on the x-axis, which again is the limit as z tends to -1. Now we have z plus 1 and the function f of z, which is all of this, 2z plus 1 over z minus 2. This time the other bracket will cancel, z plus 1, and we can evaluate this limit now. We're putting -1, so that's -2, -1 on the top, and at the bottom is -1 minus 2 is -3, and the answer for this one is 1/3. Okay, watch it, because I'm a little bit error prone with this calculations. I don't make any silly mistakes. I check my answers here, they are correct. Okay, so that's question number 1 done. And we're looking at the second question. They're quite straightforward, most of these questions that I'm doing today. There's nothing hard. You'll see much harder questions, of course, when we actually do some integration. So the second question is very similar. So f of z is equal to, so that's question number 2. We got the denominator of 2z squared minus 5z plus 2, and the numerator is simply z. Okay, factorizable with the reals probably, so let's factorize this to see where the poles are for this particular one. 2z and a z, it's a 2 times 1, I need a 2 here and a 1 here, and they're both minuses, and that should work. -4, -5, all good. So we have simple poles again on the real axis, one at positive half and one at positive 2. So we're going to use again this standard formula. So take one at a time. The residue, let's do the 2 first. The residue of the function f at 2 is equal to the limit as z tends to 2, and we got z minus 2 times f of z, which is all of that, 2z minus 1, z minus 2, cancel, cancel, and we're putting 2, so that gives us 2 over 2 times 2, 4, 2/3. Just checking the answer, it is correct. Okay, we go to the next one. The other simple pole is at half, so f semicolon of, is that semicolon or is it colon? I'm not quite sure what it is, this little thing. A half, limit as z tends to a half. Be a little bit careful here, just worth noting this. Z minus a half, and now it doesn't quite cancel the way things have cancelled up to now. It will cancel, of course, but you be careful with this because it can easily go wrong. Now, of course, which bit will cancel, this and that, but it's not quite ready to cancel. Okay, I'm gonna do it on the board in one step. I'm not rewriting all of this. So first of all, you need to factorize here a 2 outside this bracket, and this will leave you z minus a half for this particular term, and therefore we can cancel this item, this bracket. We still got a factor of 2 at the bottom, so be careful. Let me just write, I said I'm not going to write it, but I'm going to. Okay, limit as z tends to a half, and now we have z on the top, and on the denominator we have a 2 bracket z minus 2, and when putting half, we're going to get half on the top, and half take away 2 is negative 3 over 2, negative 3, so that should give us negative 1/6, and that is question number 2 done. Okay, so easy so far. It's a straightforward application of this formula. Most of the poles will be simple. Let me just move that here so I can see the next question. The next question will be different. Okay, is the sine of z over z squared. Sine of z over z squared. We can do that 2 different ways, I guess. Sine z over z squared. What kind of pole do we have for this particular one? We see the z squared there, and of course we're going to be thinking, oh, double pole. Careful, is one of the orders, if you want, of the pole is removable. So the best way to do this, so it's actually a simple pole at the origin, at z is equal to 0. I'm going to do that the first attempt by the Laurent expansion, because it's actually easier. So I'm going to write this, actually let me write on the next line. F of z is equal to 1 over z squared times the Taylor expansion of sine z, which is of course z minus z cubed over 3 factorial plus higher order terms. Okay, so I can multiply it out, so that's going to be now 1 over z, and in fact I don't even need anything else. Let me just write the terms since I wrote them there. So that's going to be minus z over 6 plus terms of higher order, z cubed or higher, and of course the residue, remember, is the coefficient of the 1 over z or 1 over z plus c or minus c or whatever it might be. So this is the residue, so it's actually 1. Okay, so, and you can also see it's a simple pole because if it was a double pole, as we're seeing the square there, the Laurent expansion would have started with something over z squared. So that's just a simple pole. So that's the quickest way to compute it. Can we do it with a formula? Okay, so let's see what happens if we use the formula. To use the formula, we have to realize this pole is actually a simple and not a double. So we have to use this particular expression. It's not that difficult. It's okay. Probably less to write, actually. So let's have a write-up for this. The residue of f at the origin is the limit as z tends to 0. And of course, we have z times f of z, which is up there, sine z over z squared. And now it doesn't quite cancel, because of course this will give us the limit as z tends to 0 of sine z over z. This will cancel, just a square. What is that now? The best way to do that is apply L'Hopital's, because of course this is an indeterminate form of the type 0 over 0, so we can differentiate top and bottom separately, of course. Okay, so the limit as z tends to 0, sine of z differentiates to the cos of z, z differentiates to the 1, and the limit of course now exists as z tends to 0. This becomes 1, and of course the residue is 1 as we found it before. So it's okay, you can do it this way, I guess. Okay, so this was question number 3, not too difficult. And we're going to look at question number 4. Question number 4, f of z is equal to e to the z, z to the minus 5. Okay, what's the best way to compute this particular residue? Probably the Laurent expansion is my preferred method for something like this, purely because it's the exponential series. It's very easy. So I'm going to write this as 1 over z to the 5. This is this bit here, e to the z. Let me write on the top like this. And now I'm going to use the standard result for an exponential, which is of course 1 plus z plus a half z squared plus the 3 factorial. I'm going to write it as a 6th z cubed. Do I need more? I need one more. 1 over 24 z to the 4, that's the 4 factorial, plus the higher order terms of z to the 5 or higher. And I don't really need to write all of this up, because the residues, of course, the coefficient of z to the 1 over z. I'm going to write it, however, just to actually see what kind of pole is that, which, as we expected, is a pole of order 5, because our Laurent starts with 1 over z to the 5. So we got a pole of order 5 at the origin. So that's going to be 1 over z to the 4 plus 1 over 2 z cubed plus 1 over 6z squared, and then we go plus, and I'm going to use a red pen, so this is the coefficient or the residue that we are after, 1 over 24 times 1 over z if you want, okay, plus dot 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 if you want. And therefore the residue for this particular function is of the pole of this particular function at the origin is 1 over 24. Could we have used the formula? Okay, we could. It's not too bad, actually. Again, the formula. We have to use the formula for a pole of order 5. So first of all, I just rubbed off the function. Stupid of me. What was it? E to the z to the minus 5. So the residue of this function at the origin is a pole of order 5. Order 5, so that's my n, if you want, on this formula here. It's going to be 1 over n minus 1, which is 4 factorial, the limit as z tends to 0. And now we have d by dz. How many derivatives is n minus 1? So we're going to take 4 derivatives, and now inside that we have the z to the power of 5, and then our f of z, which is e to the z and I'm going to write this at the bottom, z to the 5. It looks quite horrendous to start with, but it's not actually that bad, because the function we have to differentiate 4 times is in fact the exponential function, which differentiates to itself, so it could have been 100 times there. We don't really care. So the answer is 1/24, again, because 4 factorial is 24, and of course the limit as z tends to 0 of e to the z, basically, which of course will give us 1, and that is 1/24 as before. So exactly the same answer. So we've done the first 4 very, very quickly, and we got to integral number 5. Let's have a look what's on integral number 5. No, integral number 5, sorry, function number 5. We're not integrating today. F of z is equal to z squared plus 2z plus 1 over z squared minus 2z plus 1. These are perfect squares. Does it help us to write it like this on the numerator as well? Let's write it, and if we don't, we'll go back to this form. Z plus 1 all squared over z minus 1 all squared. Okay, so looking at the denominator, we have a double pole. So we got a double pole at z is equal to 1. So we're going to use the formula for this one, so where n is equal to 2. So the residue of f at z is equal to 1 is 1 over 1 factorial. I'm going to write on the first line just to see what I'm doing on the formula up there. I don't know if you can see both sides of around my face, or around my head rather. Limit z tends to 1. Then we got a differential, because the double pole is only one differentiation, and the differentiation I've got to do is of z minus 1 all squared, f of z, where f of z is of course z plus 1 all squared over z minus 1 all squared, close bracket, close bracket. Okay, this is 1, so we don't need to write anything. Limit z tends to 1. That's going, so we have just a simple differentiation of z plus 1 all squared, which is 2 bracket z plus 1. And what happens there when we put in 1, we're getting 1 plus 1 is 2 times 2 is 4. Is that a 4 up there? Yeah, that's what I've got as the answer. Okay, so that was quite simple. So a lot of this is all about just realizing which is the best method. I mean, when things get a little bit more complicated, the functions get a little bit more involved, then making the right choice how to approach it is actually essential. But these are not too difficult. So question number 6 of 8, f of z is equal to the tan of 3z, tan of 3z over z to the 4. Okay, that's a little bit annoying. How are we gonna do this? Can we do it by the Laurent expansion? The problem is I don't remember the expansion of the tan z. Can we do it by differentiation? It's gonna be even messier. First of all, the pole, the tan of z starts with z, and we're gonna have something z over z to the 4, so we got triple pole at the origin there. I don't particularly fancy using the formula for this particular one, because I'm gonna have to differentiate tans. They're gonna go into sec squared and again and again and again, but getting an expansion as well is just as painful. This probably is the most painful we've done so far. What I'm gonna do is I'm gonna get the expansion of tan of 3z eventually. So I'm gonna call g of z. G of z is the tan of z. I'm going to differentiate it. So g dash of z is sec squared z. I wish I remember the expansion now. Is sec squared z, which is 1 plus tan squared z, identity, which is now 1 plus the tan of z is of course g. So I'm gonna just drop all these arguments, g squared. Okay. Now g double dash of z. I'm differentiating that, so the 1 will disappear, so it's going to give me 2g dash. Okay, and hopefully one more term will do it, because I will hate to have to differentiate that for another 2, because the tan, of course, is an odd function, so I will need 2 more to get one more term. So this will differentiate to 2g dash, product rule there, differentiate that, leave this undifferentiated, plus leave this alone, 2g, differentiate the second, g double dash. So something like that. And let's find now, evaluate this at 0. So g of 0, g dash at 0, g double dash at 0, and g triple at 0. Okay, tan of z, of course, at 0 is 0. When we're putting 0 for that, that's gone from this bit here, so it's 1, just the 1 there. Then the next one I'm expecting to be 0, and it is, because of course g is 0, so the moment we're evaluating it is just gone. And this will be non-zero for a tan. So this has a g, and the g is of course 0, so that will go, and we go g dash, g dash, g dash is 1, 1 times 1 times 2 is 2. So I can now get the Maclaurin, or the Taylor, whatever you call it, about the origin for a tan of z. So I'm going to do it here. Tan of z, g of z is equal to tan of z, which is equal to, there's no constant term, that's the coefficient of x or z if you want. Z, there's no squares, and this is now plus 2 over 3 factorial. 2 over 3 factorial is 2 over 6, so that's a third, z cubed plus order of z to the 5. Okay, so I'm going to rub all of this off and just be left with the expansion. So far, this is the expansion of tan z. Quite clearly, if we do g of 3z, so the tan of 3z will be 3z plus 1/3 times 3z all cubed plus dot dot dot. So the tan of 3z will be equal to 3z, what's that now, 27, 9 plus 9 z cubed plus higher order terms, and we're nearly done, because of course our function is tan of 3z over z to the 4, so 1 over z to the 4, so that's our f of z. So we got the Laurent expansion basically. Okay, is going to be 1 over z to the 4 times the tan of 3z, which is 3z plus 9z cubed plus dot 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 if you want. So that's going to be 3 over z cubed, and as I said, that was a pole of order 3, that's why our expansion starts with that, plus 9 over z, and then dot dot dot, and of course our residue is of course equal to 9. Okay, just checking my answer. Yeah, it is 9. I don't have the heart to use a formula for something like this. Sorry for this one. Just Laurent is the only sensible way. I guess if you're an examiner, they give you standard expansions such as I don't know, not sine and cos, but tans and arctans and things like that. It is actually quite useful, and you don't have to derive things from first principles. Although it doesn't take that long. I mean, if you think about it, how long does it take to do this? Okay, so this is now number 6. Number 7, oh, it's a little bit long, this one. It's not hard. It's just a time waster, really. Okay, let's write it. So it's a rational, not rational, so a fraction, if you want, of complex bits. So z squared plus 4 over z plus 1 all squared with a numerator, it hardly matters, z squared minus 2z. Factorizing the numerator hardly helps, because it will not really cancel or remove anything from the bottom. This of course at the bottom is factorizes. The z squared plus 4, difference of squares, is z minus 2i, z plus 2i, and the rest of course is just exactly the same. So this is actually the function. So what kind of poles does it have? It has simple poles at plus and minus 2i from those two brackets, and it's got a double pole at -1. So we have to compute one at a time. Okay, it's going to be a lot of substitutions, and it's very likely to go wrong if you're not careful with something like this. So for this I have to be a little bit slow. So first of all, we're going to compute the residue of f at, let's go at 2i. Okay, so that is simple pole. So that's the limit at z tends to 2i. Z minus 2i times my f of z, and my f of z is going to be, that's the I there, it's going to be all of this, z minus 2i, z plus 2i, z plus 1 all squared, with the numerator z squared minus 2z. This bracket cancels, and now trying to put 2i into all of this and hopefully not make a mistake. So squaring 2i, that's going to be -4 minus 2 lots of 2i minus 4i. That's my numerator. Now I'm putting 2i there, so that's going to be 4i, and then I've got 2i plus 1, or 1 plus 2i all squared. I'm going to do an in-between tidy. I've got a factor of 4, which I'm going to get rid of because it will make my life a little bit easier. So it's going to be -1 minus I on the numerator, I at the bottom, and at the same time I'm going to square this bracket. It's going to give me 1 plus 4i, and squaring 2i is going to go 4, and it's a minus, so it's a -4. Simplify this further, -1 minus I over, I'm going to write it as 4. I'm going to do two things. This will become eventually real because of the I multiplication. So 4i times I is -4. So that's this bit here. And then I got a -3, real inside the bracket, -3i. Okay. Next, quite clearly, I'm going to lose all this into pluses. Makes it nice and easy. And now I'm going to conjugate the denominator. So 4 squared plus 3 squared is 25. So the answer is out of 25. And I got 1 plus I multiplying 4 minus 3i. Very annoyingly long and tedious, really. 4 minus 3i minus 4i, and then I've got where am I, minus 4i, and then I got I times I, which is +3, so +3 over 25, and this should give me, I'll check the answer because I'm not confident that this is correct, 7 supposed to be plus 4i there, wait a second, 4 minus 3i, this is plus there, and that gives me plus I over 25. So the residue is that, that's the residue at 2i, 1 over 25, 7 plus I. Yeah, that's correct. Very, very messy and very long. Okay, we got another one pretty much the same, is at -2i. I'm just thinking there's a quick way you can do that by replacing something for something. My brain at the moment is just dead. I cannot think, and I really don't want to do that for the other one, but I think I'll be forced to. So now the residue at the simple pole at -2i. So what I'm going to do, I'm going to sit just on this line. So I'm going to make this into a -2i, and I'm going to change that into a plus, that into a plus, and now that would have been the minus. Okay, so that's exactly the same, and we're going to try to put that stuff in and just do a lot of tedious A-level complex algebra. And we're having a -2i now, so Negative 2i, the negative will square out. The 2 will go into a 4 and the I will go into a minus. So we got minus 4 for this. Then we got minus 2 lots of that. So it's going to be minus times a minus is a plus 4i numerator. Okay, minus 2i is minus 4i at the front of this bracket. And then we've got 1 minus 2i all squared. I'm going to do the same thing as I did before. Get rid of a factor of 4. So we got minus 1 plus I on the numerator. Minus I after I remove that 4. And at the same time, let's square this bracket. So it's going to be 1 minus 2i, not minus 2i, multiply together and double. So that's going to be minus 4i, and then squaring this 4 and the I will go minus 1, so it's going to be minus 4. Okay, so what do we do now in there? Do we simplify this? I'll simplify it. Minus 1 plus I, and then we got a minus I at the front, and this is a minus 3 minus 4i. Multiply the bracket at the bottom, minus 1 plus I. Now this will become a real, so it's going to be minus times a minus a plus. I times I takes it back to minus, so it's going to be a minus 4. And this is going to be minus times a minus a plus 3i. It's very badly written. Let's write it again. That's a 4. Conjugate the denominator, so it's going to be minus 1 plus I multiplied by minus 4 minus 3i, and this is again 25 as before. And now we need to just be patient just for the last step. What times are we looking for anyway? It's very similar to the previous one. It's 1 over 25 like before, but instead of having 7 plus I, this would be 7 minus I. So hopefully you haven't made any stupid errors here. That's a positive 4 plus 3i, and then we go a minus 4i, and then the imaginary times the imaginary. I times I is minus plus, so plus 3i. I think we're in business. Okay, so the i's will go into a negative, just double checking. Yeah, it's plus 3 over 25. And as I just quoted, the residue of the simple pole at minus 2i would be 7 minus I over 25. Okay. I guess we could have actually saved ourselves some work. There's some kind of perhaps replacement we can do there, some kind of function, replace something for something, but at the moment I can't think, so I've done it the long way. Okay, we got the third pole to take care of. This pole is a double. It's a double pole at -1. So for this, we're going to have to use the formula. And for this particular one, we don't actually need this factorized like this. It will be easier, in fact, if you leave it as z squared plus 4. So I'm going to just take off the red line. Sorry, not the red line, the red writing. And now the residue at -1. Remember, that's a pole of order 2. So it's going to have 1 over 1 factorial if you want. Okay. And then we have the limit as z tends to -1. d by dz, 1 differentiation. And then we got to do z plus 1 all squared times f of z, where f of z is all of this. So that's going to be z squared plus 4 over z plus 1 all squared, and on the top we've got z squared minus 2z, close bracket. This will cancel, so that's all good. And then we need to differentiate this. Okay, so the 1 over 1 factorial we can throw away, so limit as z tends to -1, and we got to do a differentiation of z squared minus 2z. So d by dz is a quotient there, z squared minus 2z over z squared plus 4. The differentiation of that comes next as z tends to minus 1. Okay, we're starting with this on the top left, z squared plus 4. That's the ordinary quotient rule here, times the differential of this expression, which is 2z minus 2 minus, now we're differentiating this thing here, which is going to produce a 2z times the differential, not the differential, the top untouched, so that's z squared minus 2z. I don't think I'm going to do any simplifications. I'm just going to put my minus 1 in there and hopefully don't make a mistake. All squared. I think that's my bit. I'm going to write my things with red above. So what I'm going to do in there, minus 1 all squared is going to be a 1 plus 4, it's a 5. So this is this bracket here. Minus 1, minus 2, minus 4. So that's this bracket there. And z squared, so that's going to be a positive 1 for that, plus 2, that's the minus 2 times minus 1, and at the top I'm going to have a 2 times minus 1, which is minus 2, so it's going to be plus 2 lots of this, and on the denominator I'm having a 1 squared plus 4, so all squared is 25. So let's hope all of this is correct, because I'm going to cry otherwise. You're going to see a grown man cry. Okay, that is this is multiplication, so that's a minus 20, and that is 3, so it's plus 6 over 25, and please that's a minus 14 over 25. Please be right. Oh yes, minus 14 over 25 is done correctly. So that was very long. It wasn't hard. It's just very messy and very annoying, I guess. Okay, so that was number 7, by far the longest. I think it took this one longer than it took to do the first 6. I think the last one, I just glanced at it, is not hard and it's not long. So that's function number 8. F of z is 1 over e to the z minus 1. It's a little bit unusual, this one, how we're going to do it. What kind of pole is this? E to the z, just e to the z minus 1 becomes 0 quite clearly by inspection if z is equal to 0. So it's got a simple pole at the origin by the looks of things. Okay, so can we do a Laurent for this particular one? I guess we can. I'm going to actually do it differently. I'm going to actually do a Laurent for this, but I'm going to do a different method. So first of all, let's do the usual formula for a simple pole, which is here. So the residue of f at the origin at 0 is of course the limit as z tends to 0 of z times your f of z, where your f of z is basically 1 over that, so it's, we might write it like this. It's okay. So of course, when you're looking at this, this limit is indeterminate again. It's 0 over 0, because e to the 0 of course is 1 minus 1. So we're going to use L'Hopital's, and if we differentiate top and bottom separately, it will just give us the residue instantly, because that of course is 1, and e to the z minus 1 will differentiate to e to the z. And of course, as z tends to 0, the e to the z is 1, so it's 1 over 1, and therefore the residue is 1. Okay, a Laurent for this one is, the reason I'm showing is not sensible, it's just purely so you can actually see how you can get, just get some ideas. So for something like this, I will do it by involving binomial expansions. So I'm going to write this as, first of all, I'm going to cancel the 1s in front of the 1 from the exponential expansion. So I'm going to write it as 1 plus z plus z squared over over 2 factorial, so a half z squared plus dot dot dot, and then I have the minus 1 from there, 1 over, and this will cancel me the ones. So far it's going to give me a 1 over z plus a half z squared plus higher order terms. And my next step is to actually factorize on the denominator a z. So there's my z factorized out, and this will leave me a 1 plus a half z plus dot dot dot. And this is equal to 1 over z. Okay, and then of course I can write this to the minus 1, so it's 1 plus half z plus dot 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 to the minus 1. And remember, with the residue is the coefficient of 1 over z, so in fact all I want is just a constant out of this binomial expansion. I'm not interested in anything really, so it's 1 over z, and this expansion will start with 1, so I can write 1 plus higher order terms plus hot, and therefore my residue of course is 1 as before. Okay, the coefficient of 1 over z. Okay, this is enough. I think you got an idea how to compute residues. I'm sorry the lecture might have gone a little bit long and I was going very, very fast for it. Okay, on that note, who's laughing now? I'm definitely am. It's over, and I'll see you very, very soon. Join me again. Okay, bye for now.